Hi, I'm Maria Colgan, one of the product managers for the Oracle database, and I'm excited today to give you an insider's guide to the Oracle Optimizer. Now, when most of us think about the optimizer, we think about it as a black box. SQL statements come in and plans come out. But how does that optimizer actually work? Well, over the next 20 minutes or so, I'm going to share with you exactly what happens inside that box. So when we take off the lid and we look inside the optimizer, we're going to see that it's made up of three key components. The first thing the optimizer is going to do is try and rewrite your queries to allow it to be able to process it more efficiently. Once it's done that, it's going to try and generate as many possible execution plans for that SQL statement, each of which will be assigned a cost, and then it's going to pick the plan with the lowest cost. So let's dive into that first step, query transformation. What is it and how does it work? So effectively, the optimizer is trying to rewrite or transform your SQL statement into semantically equivalent SQL statements that can be processed more efficiently. That means it may open up additional access methods, join types, join orders, even eliminate some of the objects within your query if it's possible. And traditionally, these transformations were done heuristically or were heuristic based. Basically, it means if your SQL statement had a certain shape, then it would always transform that query in a certain way. But in more recent releases, those transformations have become cost-based. That means we'll look at the execution plan for the SQL statement without the transformation, and then look at the lowest cost plan with the transformation, and we'll pick the plan with the lowest cost between those two. It is, of course, fully automatic. You don't need to do anything. And there are an awful lot of different transformations the optimizer can choose from. They're well documented both in the Oracle documentation and in blogs, and I'll share some useful links for you at the end of the section. But for now, these are probably the 6 most common ones that you see there on the screen today. I don't have time to go through all of them, but I will highlight just 2 of them, just so you can understand how it works and where places you can look to see whether the transformations are kicking in your particular SQL statement. So let's take a look at subquery unnesting as our first transformation. This is going to apply to SQL statements that have correlated subqueries. Now, what does that mean? It means you've got a SQL statement where the subquery references a column from outside the subquery. So in my example here, that outside column is the customer ID. The customer ID belongs to the customer table that you see there in the outer query, but it's being referenced in the inner query. And what that means is that subquery will have to execute for every customer ID that's returned by the customer table. And if we don't have an efficient way to do that query, it could become a very expensive operation. So with subquery unnesting, what's actually going to happen is we're going to transform or rewrite that query to get rid of the correlated column inside in the subquery. So instead of it being an exist subquery, it becomes an any subquery, and the customer ID is no longer there. What this will allow us to do is execute that subquery just once. It'll return a set of customer IDs, and if any of those customer IDs match, then that particular row in the customers table will be returned. So what it is going to allow us to do, as I said, is access the sales table just once. So instead of accessing that sales table for every row in the customer table, we'll access it once. The resulting customer IDs that are returned from that subquery will be joined to the customer table via a semi-hash join, making it a much more efficient plan. I want to move on now and talk about OR expansion. That's the next transformation. What OR expansion will work on is queries where we've got a where clause predicate that has 2 or more branches in an OR statement. And the reason we want to transform these queries is that by default, the optimizer is going to look at that where clause predicate that contains the OR statement as a single clause. In other words, if I have indexes on any of the columns referenced in that where clause, I can't use them. It's operating on that clause as a whole. By transforming the query with OR expansion, what I'm looking to do is to be able to open up those access methods, be able to use indexes, but also to improve the efficiency of the query by allowing me to execute multiple branches of that OR statement concurrently so that we can improve the efficiency. So what we're going to see in the plans I'm going to show you over the next couple of slides is the transformation will use a union all statement. However, if you're on an older version of Oracle, if you're on 12.2 or below 12.2, you'll actually see the word concatenation in the plan rather than union all. So let's take a look now at what the transformed query is going to look like. As I said, the OR expansion wants to open up multiple access methods to us. So it's going to rewrite that OR statement into a union all. And that union all will have 2 or more branches. And on the second branch of that union all, we'll see an additional where clause predicate has been added automatically for us by the optimizer. Now, that where clause predicate is going to ensure that we don't get any duplicate rows. So how does it work? You'll see it's added a new function, LNNVL. What that's going to allow us to do, as I said, is to remove those duplicates, and it does it by evaluating the predicate inside that function. And if that predicate returns true, then overall that statement will return false. So in other words, if there is any product if you've got a row where the product subcategory is equal to camera media in that second branch, then it won't be passed to the union all because it would end up being a duplicate of rows coming out of the first branch. So it will just prevent any duplicate rows. If, on the other hand, the predicate inside the function returns false, then it will actually, the function returns true, allowing that row to flow into the union all. So if we take a look at how the plan differs, instead of having to do a full table scan on the products table without the transformation, what we're able to now do is utilize 2 single column indexes that we have on the product subcategory ID and the product category ID, run those index scans and do a union all of the rows returned by both of those. Now, this is also a really good example, this query, of situations where you might have multiple transformations possible for an individual SQL statement. In this case, because we've got an OR clause in our SQL statement, we could use OR expansion, as I just showed you, or we might actually be able to take advantage of bitmap OR. Another transformation. So what happens when the optimizer is faced with the opportunity to use multiple transformations? Well, just as before, it will cost all 3 options. It'll cost the SQL statement without any transformations, it'll cost it with the OR expansion, and then it'll cost it for bitmap OR. And it'll pick the one with the lowest cost. I noticed for my example query there, in the newer versions of the Oracle database, it's actually going with the bitmap OR transformation for this query. So how does that work? You're going to see the execution plan looks very similar to the OR expansion plan. We're able to access the 2 single column indexes, so for both subcategory and category, but instead of converting those row IDs into actual rows from the table, we're going to convert them into bitmaps. Those 2 bitmaps are then going to be bitmapped OR'd together, and a final bitmap will be created. Then and only then will that bitmap be translated back to row IDs, and those row IDs used to look up the final result set from the products table. So just another way to get there, allowing us to access all of the indexes, but interesting to see that there can be multiple transformations for one particular SQL statement. Where can you get more details on these optimizer transformations? Well, there is a white paper made available from Oracle called Cost-Based Query Transformations, or you can go over to the Optimizer blog, which you'll find at blogs.oracle.com/optimizer. And there's a full series of blog posts giving you in-depth understanding or knowledge of what each of the different transformations will do. You can also find details in the SQL tuning guide in the documentation. I want to move on now and talk about plan generation, because after all, the optimizer is going to generate multiple plans for each one of your SQL statements, trying to find that best or lowest cost plan. So what exactly is the plan or generation of the plan? Well, it's determining the set of steps necessary to answer your particular query. And those steps are actually a set of database operations that are either going to consume or produce rows or even do both. Let me give you a couple of examples so you understand what I mean. If I do a full table scan, that's an operation that's going to produce rows. If I do something like a hash join, that's an operation that's going to both consume and produce rows. So you see what I mean? It's just a series of these database operations that are either going to produce or consume or do both with the rows. And how is that plan generated? Well, the order of the operations and how they're going to be implemented is decided by the optimizer, and it makes those decisions using a combination of the query transformations that we just saw, as well as physical optimization techniques. When we break down the execution plan, we see 5 key decision areas the optimizer needs to make. It needs to give us cardinality estimates, decide on the access methods, look at the different join types and join methods, figure out the join order, and finally determine what kind of aggregations it's going to use to do things like sorts and group bys. But really the most important part of that plan generation is the cardinality estimates. And I want to spend a little bit of time today looking at that. So what exactly is a cardinality estimate? Well, it's the estimated number of rows each operation will return inside in the plan. And how does the optimizer calculate that? Well, it's going to determine the cardinality estimate by using the object statistics, which in conjunction with a series of formulas. So let me give you an example. We're looking at a very simple query here where we're selecting from the sales table where the product ID is equal to a literal value. Now the sales table has 100 rows in it, and there are 5 distinct values in the product ID column. So the optimizer is going to take those base statistics that we've got and plug them into a very simple formula to calculate the cardinality estimate. In this case, it'll take the total number of rows in the sales table. It's going to divide that by the number of distinct values in the column used in the where clause predicate. And the result, those 20 rows, is the cardinality estimate. Now, this is a very simple equality predicate. The more complicated the predicate, the more complicated the formula is. But the reason I'm showing you this is to make you understand just how important your base level statistics are, because they're used by the optimizer when it's doing these cardinality estimates. And the reason they are so important is because they're going to influence all the other decisions the optimizer makes, from how it's going to access the data to how it joins it, to even the join order and how it will aggregate the result set. So if it's so important, how do I know if the cardinality estimates are correct for my particular SQL statement? Well, the optimizer will actually show you the cardinality estimate it came up with for each operation in the plan in the rows column inside in the execution plan. But that's just the estimates. How do we know if the estimates are actually correct? Well, you can add an additional hint to your SQL statement called gather plan stats. What that's going to do is it's going to ask Oracle to persist the execution statistics it's going to see when that query executes, and it's going to put those execution stats into the cursor inside the shared pool. That way we can go back and we can look at what actually happened during the execution and compare it to what the optimizer thought was going to happen. So how do you do that? As I said, you're going to add the gather plan stats hint to your SQL statement. Go ahead and execute that statement, and then use the DBMS xplan display cursor function to actually show you the plan. We're going to add an additional format parameter to that function call that's going to be called all stats last. In other words, give me all the execution statistics for the last execution of this particular cursor. That's going to change the execution plan that you see. Instead of having a single rows column, you end up with 2, one called the E rows and one called the A rows. E rows, estimated number of rows. A rows, actual number of rows seen during the execution. The two columns are right next to one another inside in the plan, so you can quickly scan down through those columns and see how close the estimates were to the actual number of rows. Now, they don't need to be identical, but you do want them to be in the same ballpark. That means the same order of magnitude. So in my example here, it looks like we have a serious misestimate for the products table because we thought we were getting 41,000 rows. We actually only got 1,000 rows. So that isn't something, if I had a plan I wasn't happy with and I wanted to investigate what's going on, investigating why the cardinality estimate for the products table is off would be the first place I'd start. If you're taking advantage of one of our cloud services and you're more used to interacting with the database through a UI, whether that's one of our own, like SQL Developer, or if you're just interacting with it through the console, you can get access to SQL Monitor reports. This is basically a GUI version of the explain plan that we've just been looking at. But what's great about the SQL Monitor reports is the fact that they always show you estimated rows versus actual rows. And that way you can compare the values straight away. You don't need to add any hints. You just need the statement to be one of the high load SQL statements. If it's not, then you can add the monitor hint to your SQL statement and have us automatically capture the SQL Monitor report for you. So if cardinality estimates are so important and I look in the execution plan and I find I have a problem, the cardinality estimate is wrong, how do I go about correcting that? First place you want to look is at your statistics. Do you have an accurate or representative set of statistics for the objects being used in that query? If you don't, then you need to gather a new set of stats for those objects, and you can do that very easily using the DBMS stats package that we supply with the database. If your stats look okay, one of the other reasons why you might get a cardinality misestimate is if there's a data skew in one or more of the columns inside in those tables. In other words, one or more values are popular while other values are less popular inside in those columns. So easy example, we sell much more of one product than we sell of another, or all of our customers live in the zip code closest to our store. We don't really have many customers in other zip codes. Things like that cause a data skew. And if you remember when I showed you the formula for how the cardinality estimate was calculated, you'd realize that the optimizer assumes uniform distribution of rows across the number of distinct values in a column. So if you don't have that, if you do have a data skew, then you're going to need to create a histogram to let the optimizer know about the data skew. So how do I create a histogram? Well, they're actually created automatically for you if you let all of the parameter values go to the default when you use the DBMS stats packages to gather your stats. If you don't, then make sure you manually create the histograms for those columns with the data skew. If there's nothing wrong with your stats and you've got all your histograms in place, take a closer look at the SQL statement, because the problem for the cardinality estimate may be being caused because we're applying a function around one of the columns used in that where clause predicate. As soon as you wrap that function around the column, the optimizer has no idea what that function will do to the number of distinct values in that particular column. It may increase it, it may decrease it, it may not change it at all. But the optimizer doesn't know, and so it needs to make an estimate or a guess. It can no longer rely on the base statistics. And as soon as the optimizer starts guessing, you know you're going to be in trouble. So how do you fix that? Well, traditionally, the old-fashioned advice would be to create a function-based index on the column that you're wrapping in the function. If you don't want to create any additional indexes, after all, you do need to maintain that index for any DML operation, then you can take the new approach that's there from 11G onwards, which is to create extended statistics. So you create statistics or gather stats on the function wrapped column so the optimizer knows exactly how that function impacts the number of distinct values within the column. If you don't have any of those issues, then maybe you need to take a closer look at the SQL statement and see if we're using multiple columns from the same table in the where clause predicate. Now, when you go to SQL school, you're always advised to filter out as many rows as possible that you don't need. So adding multiple predicates from a single table is not a big deal. In fact, it's normally recommended. And by default, the optimizer assumes each additional where clause predicate you add to your SQL statement is actually going to help reduce the number of rows being returned from that particular table. The problem is sometimes our columns have a real world relationship or have some kind of correlation that those additional where clause predicates don't actually reduce the number of rows being returned. And so the optimizer comes up with the wrong cardinality estimate. Quick example of this would be if I said, I want customers where the city is Las Vegas and the state is Nevada. If that was the query I had, we know that Las Vegas is only in the state of Nevada. The optimizer doesn't. It's going to assume that additional where clause predicate on state will reduce the number of rows being returned, but of course it won't. So how do I tell the optimizer about those real world relationships among the columns in my tables? Well, again, I'm going to take advantage of those extended statistics and gather stats on that group of columns as a whole so that the optimizer knows exactly what the cardinality estimate should be for queries where I'm using those multiple columns together. Last possible case can be if I'm using complex expressions inside in those SQL statements. In other words, I'm using multiple columns from different tables in an expression in the where clause predicate. I don't have a magical set of stats for this one, I'm afraid. This one, you're going to need to take advantage of dynamic sampling. Dynamic sampling allows the optimizer at parse time to take a small sample of rows from the objects, apply the function that you're using to those values, get a result, and then based on that, it will extrapolate how many rows it believes should be returned in the full data set with that particular predicate. Now, if you are going to use dynamic sampling for these complex formulas, then make sure you're setting it to level 4 or higher. Now, as I said, cardinality estimate is the most important part of the plan generation, but there are 4 other decisions the optimizer makes. I don't have time to go through those today, but I will share more resources for you at the end of this section so that you'll know exactly where to get a lot more detail, whether you want it as white papers, blog posts, or videos. But before we move on from the plan generation section, I do want to highlight the fact that there is a lot of additional information underneath the plan itself, where the optimizer is going to share details on how it's made the decisions and what additional information impacted that. So let's take a look at an example so I can show you more about what I mean. If we look at this sample plan, you see there the plan table that we're all very used to looking at, but underneath that there are 3 key sections you need to be aware of. Underneath the plan table, you see the predicate information. And if you remember back to when we were in the transformation section, that was one of the places you could tell the transformations had kicked in because the additional where clause predicate the optimizer added to our statement showed up in that predicate information. You also want to look there to see whether or not your where clause predicates are being used as access predicates, in other words, being used to go and retrieve the data, or if they're being applied as filters. In other words, they're only being used after the data set has been fully retrieved from the base objects, and then it's being filtered out. So ideally, you want to see most of your where clause predicates used as access predicates. Starting in 19C onwards, there's a new section underneath the plan. It's called the hint report. It's going to let you know what's happening with the hints that you used in a SQL statement. Are those hints used? Was there an error, as there was in my case, a syntax error in the way I specify the hint? I misspelled the hint and therefore it's not valid. So even though I think, oh, the optimizer is simply ignoring my hint, it's not actually ignoring it. It couldn't use it because I spelt it wrong. The final section is the note section underneath the plan. It's going to tell us things like dynamic sampling was used because maybe I'm missing or have inaccurate stats for this particular SQL statement. It'll tell me whether this is an adaptive plan, a plan that may change while the SQL statement is actually executing. It'll tell me if some kind of SQL plan baseline or a profile was used for that particular SQL statement. It'll also tell me whether parallel execution was used and what parallel degree was used for the SQL statement. So a lot of useful information there in the notes section to help you understand exactly how this plan came about and what kind of plan it really is. So to get much more information on how the optimizer makes the additional decisions in the execution plan, and to understand how to read and use those plans to help you tune SQL statements that are underperforming, take a look at the white paper, Oracle Optimizer Explain the Explain Plan. I have a blog series on my own blog, sqlmaria.com, that goes through each of those decisions in a lot of detail. And there's also a video series that accompanies those blog posts. So if you'd rather watch more videos, head on over to my channel on YouTube and you'll be able to get all of that information. Let's move on now and look at the last part of the optimizer, the cost estimate. So the cost is going to represent the unit of work or the resources needed to execute each of the operations in that plan. And the optimizer defines that cost or that unit of work using both CPU and disk IO. So how much CPU or disk IO is needed to execute this particular step in the plan. Now, the total cost for the plan is the cumulative cost of each of the operations. There's also sometimes we'll add some additional cost to apply filters and things like that that are not necessarily visible in the previous steps of the plan, but effectively that's what it is. It is the optimizer's estimate of how much resources are going to be needed to execute this plan. Now, if you're wondering how we came up with how the optimizer should work, all of that goodness, if you're interested in the history, the Oracle Cost-Based Optimizer is actually based on a research paper that came out all the way back in 1979. And in that paper, it outlined what a good cost-based optimizer would do. And as you'll see, we're sticking very much to that formula. The paper says you produce multiple execution plans for each of the SQL statements. You estimate a cost for each of those plans. And then the optimizer picks the plan with the lowest cost. And that's exactly how it works today. I also want to give you a quick warning. Don't get too hung up on understanding exactly how the optimizer came up with each individual cost in the execution plan. The reason I say that is the cost is really there for comparison purposes. So you can use it to compare one plan versus another, to see whether it appears more efficient or less efficient, but it really isn't there to fully understand and be a hard calculation that you need to worry about. So as we wrap up, I want to leave you with some of my top tips for being able to get the very best out of the optimizer with minimal effort. First and foremost, I want you to help the optimizer help you. And by that, I mean, you want to share all the information you've got about your particular environment or your particular workload. So always make sure the optimizer has a representative set of statistics for all of the objects in your schema. If you know that a column will never be null, make sure you set the not null constraint so the optimizer also knows that information. If you know a column is unique or is a primary key, specify the constraint so the optimizer also knows that. Same is true for primary key, foreign key constraints. If you know that a column relies on another column from a different table, create the foreign key constraint so the optimizer knows it too. When it comes to diagnosing poor performing SQL statements, really utilize the execution plan to help you. It's got a lot of information about what's going on in that SQL statement. Make sure you not only look at the operations inside in the plan table, but also look underneath it for the predicate information, the hint report, and of course, the notes section. And finally, if you are going to leverage hints, please do it with extreme caution. Make sure that instead of just adding one hint to influence just one decision, think about using a complete outline for the plan, a complete set of hints using a SQL plan baseline. If you have used hints in the past and you're looking to upgrade to 19C or very soon, if maybe to 23C, Take advantage of the underscore parameter optimizer ignore hints during your testing to see whether or not you really need those hints in the newer versions of the database, or if they can be removed as part of your upgrade. I want to thank you for spending time with me today. I hope you found this session useful. You can get a lot more information on the optimizer by going to my blog, sqlmaria.com, following me on Twitter, taking a look at the videos on YouTube, or connecting with me on either LinkedIn or Facebook. Either way, I hope you enjoy the session and you enjoy the rest of the conference. Thank you.